So we've seen that our conservation of energy equation, or the energy balance equation, whichever way we want to label it, is the way that we have kept track of energy for a mechanical system. And I can rearrange this equation. So if I take my two initial energy terms over here on the left and move them over to the right, I've got final minus initial kinetic energy plus final minus initial potential energy. This term is delta K plus this term is delta U, and delta K plus delta U is just another way of saying the change in the total mechanical energy of our system. So what this equation has been highlighting is that keeping track of how the energy changes for your mechanical system is all about keeping track of the work done on the system by non-conservative forces. We said conservative forces, they do work to change how the energy is stored within your system, but non-conservative forces do work to change what the total energy is. If the work done by non-conservative forces is zero, then the total mechanical energy of your system doesn't change and we have conservation of energy. In thermodynamics, we have a very similar equation. So this equation is the first law of thermodynamics, and what it tells us is that the change in energy of your thermodynamic system is equal to the energy transferred into or out of your system as heat minus the work done by the system. What the first law of thermodynamics is telling us is that keeping track of how the energy changes in a thermodynamic system is all about keeping track of two ways that energy can be transferred into or out of your system. It can either be transferred into or out of your system as heat, that's the Q term, or it can be transferred into or out of your system through work. And we'll talk a little bit more about this work term in a minute. First, let's focus on the heat term. So again, Q is energy transferred into or out of the system, and so that term is going to be positive when energy gets transferred into the system. Q will be negative when energy is transferred out of the system. So the convention that we've been using since we started working thermodynamics problems, that still holds when we're using the first law of thermodynamics. When we think about this work term, well, let's start by being clear about the fact that there are two ways that we could choose to define this work. We could talk about the work done by the system or the work done on the system. And those two things are related to each other. In fact, the work done by the system is simply negative the work done on the system. And we'll talk about where that minus sign comes from in a second. There are plenty of places where you can run into the first law of thermodynamics so that it's been written such that this sign here is a plus sign rather than a minus sign. So it says that delta E equals Q plus a work term. And that's still a perfectly valid framing of the first law of thermodynamics. It's just that that work term, when you're adding it, is the work done on the system, not the work done by the system. So we have to be very clear about which one of those we're picking, and in working problems we're going to pick the work done by the system. So where does this work come from? Well, so let's think about a system here that's sitting inside some cylinder. There's a piston head that's holding that system inside the cylinder. So the system's represented by the blue here, the piston head, and the piston head can move. Because my system inside the cylinder is at some pressure, that pressure is going to generate a force against the piston head. If my system expands, the piston head moves from the location where it's pictured to this second space represented by the dotted lines. The volume of my system is increased, so my system has expanded, and the force and displacement point in the same directions, so that the work done by the system in that case had to be positive. The work done on the system would be negative. On the other hand, let's say that my piston started out here at the dotted lines and moved in to where it's pictured. So in that case, the volume of my system has decreased, the system has been compressed, and because now the force and displacement point in opposite directions, then the work done by the system would be negative. But why is it that the system was compressed? Well, it was compressed because there was some external force out here that pushed harder than what the system pushed that caused the piston to move in. That force did work on the system, and that work was positive because the force pushing on the system pointed in the same direction as the displacement. So where this minus sign comes from is that if you think about what's going on with this piston head, there's a force by the system that pushes to the right, but there's a force on the system, acting on the system, that pushes back to the left. Those push in opposite directions, so whichever way your piston head is displaced, the work done by the system versus on the system, one will simply be negative of the other. Part of why we're going to focus on the work done by the system is because it's simply a little bit easier in terms of the way that we'll see things in a minute talking about PV diagrams, to think about how the work done by the system will be positive as the system expands. So if we think about our definition for work, so the work done by some force is equal to an integral, and we'll just go ahead and say that this is a one-dimensional situation where the force only exerts in x, therefore we don't care about the displacement in x, and so from some initial to final position we need to integrate that force over the displacement. So we know that we want to graphically interpret this integral equation by telling us that the work done by the system is equal to, the integral sign says the area under the curve of, put the fx on the vertical axis and x on the horizontal. So that the work done by the system is going to be the area under the curve of a x component of the force versus x position plot. Well, if I take that equation and I can multiply it by the number 1. It's just here I've chosen a unique version of the number 1 that happens to be the area the force is exerted over divided by the area the force is exerted over. And all I'm going to do is I'm just going to choose to rearrange those two area terms so that the one on bottom gets paired with the force term and the one on top gets paired with dx. And the reason why I do this is because force per area is the pressure. And area times some tiny little change in length, so this is a length times area, that's a volume. So the area times dx is dv. It's a differential volume element. And so I can rewrite my equation as some integral from an initial volume to a final volume of the pressure times my differential volume elements. In terms of thinking about what this equation is telling me graphically, I want to read this the same way I did the equation for work up at the top, which is the integral says it's the area under the curve. Now I want to put pressure on the vertical axis and volume on the horizontal axis, so the work done by my system has to be the area under the curve in a pressure versus volume plot, and this is what's known as a PV diagram. So part of why we're going to care so much about PV diagrams when we're dealing with thermodynamic systems is that thinking about the area under the curve in a PV diagram tells you the work done by the system. Again, we're choosing to focus on the work done by the system simply because we know that when our system expands, then that term's going to be positive. So if in moving from some initial state to some final state, whatever the process is, if your system expanded in doing that, then the work done by the system will be positive. So it's just easy to read what the sign should be for the work done by the system off of a PV diagram. So having talked about these two individual terms on the right side of the equation, again, let's come back and think about what our first law is trying to tell us big picture. So again, it says you can change the thermal energy of your system in one of two ways. An energy transfer as heat, or by work being done either by or on your system. And so what this means is the internal energy of a system can be increased when energy is transferred into the system as heat. So if your system absorbs in energy as heat, or when work is done on the system. Again, that would be a Q plus work on, and the work on being positive means that you're increasing the internal energy of your system. The internal energy of your system can be decreased if energy is transferred out of your system as heat. So energy is lost as heat, or work is done by the system. There are two ways that we can change the internal energy, and so what we'll end up seeing is that depending on the process we choose, what delta E ends up being is really the interplay between whether each of these terms are positive or negative. So as an example, we're going to talk about a process where the total energy change of the system is zero, because the system is taking energy into the system as heat. So there's a positive Q, but it's also doing positive work. So positive work is being done by the system. And if all the energy it takes in is basically converted into work, then the total energy of your system doesn't change. So it's the interplay between these two terms that's going to tell us how the total energy of our system is changing.